Hello everyone, this is the second part of logistic regression. This video replaces our regular lecture in the classroom. Let's get started. Before we get into the new materials, I would like to do a review. This is on linear regression versus logistic regression. So how are they different? When we have linear regression, our response variable y is quantitative. I mean that they have meaningful values, meaningful numbers as their value. For example, height or age. Versus in logistic regression model, your response variable is binary. It could be yes or no, or male or female. We usually use the binary code 0 or 1 to represent it, but know that it's actually representing two categories. In linear regression, the population model format is expected y given x equal to beta 0 plus beta 1x. So we can see that beta 0 plus beta 1x is modeling y, the response variable, directly. Not so in logistic regression. So here is the formula for logistic regression. We can see that on the left side, it's much more complicated. And beta 0 plus beta 1x is actually modeling the log odds of y instead of y directly. And this part in the parentheses is odds. If you forgot why this is odds, please review lecture 1, part 1 of the logistic regression model. I'm going to show you a table. In this table, I'm going to summarize a few quantities related to logistic regression model. The first one is probability. The second one is odds. And the third one is log odds. So if our y is binary, then the expected value will be the probability of y equal to 1, or sometimes we call it the success probability. So when we have the success probability and divided by the failure probability, it becomes the odds. Finally, by applying log to the odds, we have log odds. What are the ranges of these quantities? The probability has to be between 0 and 1, otherwise it would not be meaningful. Log odds, though, it will always be a positive number, but it can range from a very small positive number to positive infinity. In sports commentary, you may hear comments like the odds of winning for the Vikings is 3 to 1. So 3 to 1 equal to 3 is a positive number. If you take a log to the odds, then the range becomes the entire real line. It can range from negative infinity to positive infinity. So the benefit of using log odds on the left side of the equation is that the right side of the equation, beta 0 plus beta 1x, also could range from negative infinity to positive infinity. As you can imagine, this line can go very high and then can go very low depending on the value of x. So here is a quick review of linear regression versus logistic regression. The dataset we used in the first lecture was from the Challenger spaceship. Remember, inside this dataset, we have temperature, and we also have whether or not there is damage to an important component in the rocket called O-ring. So I have visualize the data in this graph. And you can see that some of these data are jittered slightly up and down so that these individual observations could show up better in the graph. For example, when the temperature is about 67, we have about 3 observations at the same temperature. And if I don't jitter them, meaning if I don't slightly move them up or down, we might not be able to see all of them. So this is just a tool for visualizing the data. Let's see what happens when we fit a linear regression model to this data set. So this will be the fitted linear regression model, and I also have the equation for the fitted model. 2.9 minus 0.037 times the temperature. But we can see that this straight line is too rigid for our data set, and we want it to be able to bend. So here comes logistic regression model. We have temperature, and then we have O-ring damage here. Again, 1 means there is damage, and 0 means there is none. This is our fitted model using y hat, or the estimated probability of having damage at the left side of the equation. So you can see that it's not a linear equation. That's why it's a curve in the graph instead of a straight line. Alternatively, you can write it down in this way: log odds equal to 15 minus 0.232 times temperature. We discussed how different quantities change when the temperature increases. Specifically, we said that the log odds is expected to decrease when temperature goes up. This is because, according to the fitted model, log odds, we see that when x increases, the log odds is going to be decreasing. We have discussed how the expected odds will change. It's also decreasing. So if we take the odds by applying exponential to both sides of the equation, this is what we get. And we can see that when x increases, the power of E will decrease, and the entire value, meaning the odds, will also decrease. What about probability? Turns out that probability will decrease as well. So this is the formula if we have probability on the left side, and the denominator will increase when x goes up, so the entire thing will decrease. The takeaway from this exercise is that the log odds, and probability will go in the same direction. So if you know that the log odds is decreasing, you should immediately know that the probability and odds are decreasing as well. Now let's actually interpret the model coefficients. We have talked about how log odds, and probability will change when x increases, but how exactly are they changing, or how fast are they changing? Now let me put the formula for log odds, and probability in the box. So I have grayed out the odds, the formula for odds, because this is less often used. We usually use the first one, the log odds or the probability. Now let's say I increase the temperature by 1 degree. What happens to different quantities? First, consider log odds. This might be pretty straightforward. We just say the log odds is expected to decrease by 0.232 because our coefficient beta 1 hat is equal to minus 0.232, so it's a decrease, and then the amount of decrease is 0.232. So this is the amount of decrease. Now, how does the odds change? I actually encourage you to stop the video here and try to think about how you will answer this question, and then you can come back and check the answer. All right, the correct answer is 20.7%. It's going to decrease by this percentage. And how do I get 20.7%? This is by taking e raised to the power of beta 1 and then minus 1. So how do we get this value, and why does 20.7% represent the percentage of decrease in odds? To answer this question, we are going to do a little bit of algebra. So this is odds, my fitted model written in terms of odds on the left side. Consider two observations. The first one I use 1, and the second one I use 2. So odds 1 is equal to e raised to the power of 15 minus 0.232 times x1, and odds 2 is equal to e raised to the power of 15 minus 0.232 x2. Now what I'm going to do is to divide both sides. So odds 2 divided by odds 1, and then the right side is divided accordingly. The benefit of doing division is that I can cancel out certain information. But before I do that, let's suppose that we increase the value of temperature by 1. So x2 is equal to x1 plus 1. We replace x2 with x1 plus 1. And then we could cancel out certain values. And eventually, we get e raised to the power of minus 0.232. And remember, minus 0.232 is beta 1 hat. And this is equal to 0.79. So hence, if we subtract 1 on both sides, the left side becomes odds 2 minus odds 1 divided by odds 1. So the increase in percentage of odds. And then on the right side, we have 0.793 minus 1, which gives us decrease by 20.7%. So this is how we derived or justified their interpretation on the top of the page. Did you get it? So the next example is on smoking and mortality. In this example, I'm going to include more than one predictors into our logistic regression model. First of all, the backstory of this dataset is based on a very old study. In this study, women were interviewed about whether or not they smoked. And then the outcome variable records whether they were still alive 20 years later in a follow-up study. So this is what the data looks like. So we have the smoking status, yes or no, and then the age at the time of the first interview. We also have outcome, dead or alive. So for example, in the third case, there was a woman who was 71 years old at the time of the interview, and 20 years later, the outcome was recorded as dead because she was no longer alive. We will fit the logistic regression model to predict the outcome based on smoking status and the age. So we know that age is an important factor for mortality. The older you are, the more likely you are going to be dead. So just according to the natural rule. And we are also interested in how smoking affects mortality. In order to run the model, I will generate a new variable called outcome number, basically. So using 0 and 1 to represent the outcomes. So alive will be 1, and then dead will be 0. So in the first 6 observations, 5 of them are actually were still alive 20 years later. So visualization for the data set, I was able to separate the smoker and the non-smokers. So in the top graph, we have the smokers. We can see that as age increases, generally speaking, more of them are dead than alive. The same goes for the non-smoker group. When age increases, there are more people dead than alive. We could use the following code to fit the model. Remember to use GLM because it's generalized linear regression model, and set family equal to binomial to tell R that you want logistic regression model. The syntax of the formula y tilde x1 plus x2 is basically the same as linear regression model. and then we can have the summary. So here's the coefficient table, partial summary from the model. So we can see that the intercept is significant, and the age coefficient is also significant, a very small p-value. However, the dummy variable based on the smoking status, smoker yes, has a very relatively large p-value, 0.224. Perhaps smoking does not have an effect. Perhaps this data does not support the idea that smoking affects mortality or smoking is significantly associated with mortality. But for now, we will write down the fitted model according to the estimated coefficients in the table and not removing any variables. So this is the fitted model. We have the intercept, minus 0.12 times age, minus 0.20 times smoker yes. Given this fitted model, let's interpret the model coefficients. So first, let's talk about the slope coefficient of age. How do I interpret minus 0.12? So I'm going to give you some structure. Because we have more than one predictor variable, you have to say holding smoking status constant, because you don't want the smoking status to change at the same time. So just like in linear regression, multiple linear regression, you have to say holding other variables constant. Here we have to say basically holding other variables constant, which is smoking status. And when we increase x by 1 year, age increases by 1 year, the odds of survival is expected to. Think about how you would interpret this. You can stop the video here and then come back when you have the answer. So this is the answer. We can take exponential, then the coefficient for age, minus 0.12, and then minus 1. So it will be decreasing by 11%. Did you get the correct answer? Next, let's consider interpreting the estimated slope coefficient of smoker yes. Again, I'm going to give you the structure, this time holding age constant. Because smoker yes is a dummy variable, so effectively we are comparing two groups, the smoker group and the non-smoker group. When compared to the non-smokers, the odds of survival for smokers is expected to. You can pause the video here and think about how you would answer this question. The correct answer is minus 0.18, so decrease by 18%. We basically use the same method. So knowing how to interpret coefficients in logistic regression model is important, and it's definitely something I will be testing in exam 3, so make sure that you understand how to do that. And finally, let's look at a graph for the models. So I'm going to show you two curves. This is age versus probability of survival. So I removed the observations, but I have included two curves, and one of them represents the smoker group and the other one represents the non-smoker group. Can you identify which curve represents the smoker group? One way we approach this problem is by thinking about specific age levels. For example, age equal to 60. According to the fitted model, we can obtain the log odds for smokers at 60 years old. So if we put in age equal to 60 and then smoker yes equal to 1, we get 0.2 as the log odds. And this can give us the probability of survival for smokers, which is 0.55. We could do the same for non-smokers, and their log odds is 0.4. And then their probability for survival is 0.60. So we can see that at least at age 60, non-smokers will have a higher probability of survival than smokers, which means the dashed line represents the non-smokers and the solid line represents the smokers. We could also look at the coefficient of smoker yes. It's a negative coefficient, which tells us that when we hold the same age or hold in age constant, the smokers will always have a smaller log odds for survival than non-smokers. And remember previously we talked about odds, log odds, and probability going in the same direction. So having a smaller odds for smokers means that the smokers will also have a smaller probability for survival. Hence, their model or their curve will always be below the non-smokers. So we have non-smokers on top and then smokers in the bottom. Alright, this is the end of our lecture, and on Friday we will pick up from here. So the takeaway or the important takeaway is how to interpret the model coefficients in logistic regression model, and also how to identify curves inside the graphs if we have multiple groups inside the data. I thought I have already recorded. Have I recorded it?